Hello, everyone. It's great to be here. I was told that there was a VR talk at the same time, but it's not there anymore. So I feel like this helped fill in the room. I'm not responsible for the other talk to be canceled, just so. But apart from that, it's good. All right. I'm Claudio. I'm here to talk to you about Elixir. So that's the company I work for, Erlang Solutions. I do Elixir full-time. The majority of the work we do in terms of consulting involves helping companies adopting the language, work with them for a few months, and then they work on their own. So there's pretty much the majority of my time is spent getting a lot of people up to speed with slightly more advanced uses of the language. So they can definitely start learning on their own, but then when you want to grow beyond a small toy application, that's when we usually come in. So what I'm going to talk about today is kind of the result of the things that I've seen in the last few months in terms of adoption of the language. Now, the first thing actually that I want to mention is that, first of all, I'll start with a question, like who's tried the language? Who has tried the language or spent a bit of time with it? Okay, that's good. This is not an introductory talk, in the sense that I'm not going to tell you, hey, this is the language and this is how it looks like. I feel that that topic has been covered already in a lot of talks that you can definitely find online. What I feel like is lacking is conversation about, okay, I get that part, I get how it looks, and I get the basics. How do I do more complicated things? Or why am I getting stuck at this point? So if things today don't make a lot of sense, I hope that you can just like freeze this, like keep it there in the freezer for a few months, and then if you come back to it with a bit of more initial knowledge, then you can say, okay, now I understand why that was useful. If that doesn't happen, that's fine anyway. There's always a good chance that I'm just doing it wrong. So let's just like pretend that at this point everything is still working properly. So the original title of this talk was Idiomatic Elixir. As you would expect from many talks, you start working on it and then you figure out that the title actually could be better. So what I went for in the end was, instead of Idiomatic Elixir, and I think flexible Elixir is better. Now, why flexible? So as you do, you start with a dictionary. Flexible, there are two qualities for when something is flexible. It's able to change easily according to the situation, where in this sentence you can replace a situation with requirements of business objectives, or whatever you want. So the first thing we want from a language, or something where we basically invest a lot of time and energy, whether it's for learning or working with it, is that it doesn't lock us into predefined patterns or ways of building things that make it more difficult than it should be to change over time. Now, the problem with that is that more often than not, change doesn't come for free. Like you change and then, I forgot who said that, like move fast and break things. Not really. Like you can move fast without breaking too much if what you use allows you to move and keep some sort of resilience that just keeps things running more smoothly. And that's what, I think these are two qualities at the end of the day that I think they should be a requirement of anything that we use. But at the same time, I haven't found anything else yet that has them as so ingrained in the language as Elixir, or by extension Erlang and the Beam virtual machine. So fair warning, there will be code in this talk. I understand it's the last talk of the day, so if at any point I see heads slightly bending, it's fine. It's okay. So let's start with the first use case. You got an application where you want to handle volatile data. By volatile data, we mean data that if it gets lost, it's not that big of a deal. So it could be caching data, it could be data that could be recomputed from a permanent data store, anything that kind of fits this, this model. Now, if we follow the example, we can talk about a cache store. So how many people have implemented a cache store in any language, in any application they worked on? Okay, that's okay. So the use case should be familiar. Now, this is a simplified cache store. It doesn't have the whole fetch, and then if the key is not there, I'm going to compute the value and store it. It's a cache store that just has a get and set operation. Now, because everything in Elixir and Erlang is backed by processes, if you want to build a cache store, it will be under the hood, and you don't have many options around that. It will be a process. So it's somebody you start, you keep it running. As long as it keeps running, then it can hold data. And that data is inside that process. So that memory space is exclusive for that process. If you want to access it, you have to talk through the process, send messages to read it, and possibly write it. So there is a built-in level of protection around memory because no state is shared between processes. So if we keep in mind this, this API, a classic way to build this thing in Elixir especially is by using a construct called agent. So you can think about an agent as a box where you start, and then you start as like any other process. You put it inside your supervision tree, which is a way to handle recovery from failures. Things run, they are supervised. If they fail, supervisors restart them. That's the whole principle behind the resilience on the VM. So an agent is a box. An agent holds data, holds state. It has a generic API to access it, but you back it with the data structure you want. So it can be used for anything. It's a very straightforward way to build a key value store in memory because it is, if we look at the API of the agent, a superset of the API we want to support. We have get and set. An agent has all sorts of other operations for a particular form of updates or different guarantees you want when you do these types of updates. So you can use it. And this is the entirety, by the way, of the implementation of this thing. Like if I can safely say it fits on 2 slides, and that's complete code. It has all sorts of advantages because it's very easy to understand in the sense that once you know the primitives, it is very repetitive operations. But it does come with a few caveats. Now, let's look at the pros and cons with this. So it's a simple implementation because it's short and you use only one specific construct that you need to know about. It's also strictly consistent because each operation is queued. Each process, all processes in Elixir have a worker based on a message box. So the mailbox receives messages and they're processed in order, one by one. So if you implement any kind of operation like agent does on top of that idea, then writing happens before the subsequent read, that happens before the subsequent write, and so on. So at any point in time, any operation will happen with a steady state of the world. That's the data at that point in time. It's not possible to have concurrent reads and writes in that process. So it's strictly consistent. Now, this is exactly the major downside. You do one operation at a time. So if you've got an entire application depending on a cache store that does one thing at a time, this will become a performance bottleneck. And because the language itself, in terms of reading things in and out of memory, is fast enough, this is not the kind of thing that you notice in development. Like, this is the kind of thing you notice if you do serious load testing or if you run in production after a while and things slow down and you start to wonder why. The other thing is data, any form of data that is kept in memory in the language is associated with the process that builds that data. In other words, memory is owned by the process. So if this agent process holds a huge amount of data in cache and the process crashes, that data is gone. It's instantly garbage collected by the runtime, and you just lost it. It's volatile data, but the act of rebuilding that data set is potentially very expensive. So while you don't care about the data in itself, you may want to care about the consequences of losing it in terms of rebuilding it. So what people do at this point is, when they start to read about this, they come across with this pattern, which is using a GenServer, which is a shorthand for generic server, plus another data structure that comes with a standard library in Erlang, which is the ETS, which stands for Erlang Term Storage. And I'll introduce them both briefly. So GenServer is a generic server behavior, means you use it as a construct to model a relationship between a client and a server. So you're a client, you want to do some operations, you talk to another process which acts as a server. The server knows how to mutate and operate on the data that it holds, so it gives you an API to do it, and you call that API. The ownership of the data is in the server, so you use it, and when you use it, you copy it over, and that data is immutable. So at any point in time, if you do something wrong with the data on your side, I shouldn't do that, on your side, the data is safe in the server process. This description is, I don't know if it's self-apparent, but the agent is built on top of this. So agent is a specialization of this pattern. So it's a server that gives you an API to access the data. But you can use generic servers to build pretty much anything. It is by far the most common way to approach the majority of the problems you have when you want to build anything in Elixir or Erlang. ETS stands for Erlang Term Storage. It's built, as I said before, it's built in. It's an in-memory data storage. Basically, it's a key value store where the shape of the data you put in the store is not predetermined. It can be any valid type that you use in the language. And when you use the table, you define the way the table understands the data. So for example, if you have a tuple with 3 elements and the second element is your primary key in that data, you can tell, hey, table, this is going to be the type of data you receive. Use that specific field as a primary key. So it gives you a lot of flexibility. It has the property of having constant time access, so which is what we want from a cache. In other words, no matter how big the data set is, to read it or write it, it's a constant time operation. So if we use that and we approach the problem, we say, okay, we want to start this cache store. I want to start using this one of these ETS tables. So I use that, I do that, started with that. I have to set some properties on this table that are related to who can read it and what kind of optimizations you can use with it. But suffice to say, you have a way to say, okay, this data I have in this table, I want to make sure that many people can read it at the same time. So you can set up, there's an option called read concurrency for that. I want to make sure that it's public so that all processes in my system can read it, because that's not data you need or you want to protect at that point. And you can also, because you want to optimize for reads more than writes, a cache store normally is, unless you're doing something radically different, but normally you have many more reads compared to writes. So you can still model the problem in terms of, I'm going to use a GenServer, which is a sequential process. It has the same characteristics as an agent. You do things one at a time when you go through it. So you can write to the cache store in a more sequential way through the GenServer, which means that you pace your writes, but then read directly from the table, so that you can read as much as you want, and you get much more performance. And this is good because if you start writing too much in one single shot, that kind of affects the performance of the reads as well. So when I say performance, I know that it doesn't mean anything by itself. You definitely need numbers for this. We're talking about using data structures that would become a problem in terms of scaling beyond at least a few thousands of requests per second in terms of public API usage. But you could go easily, you could go to like 40, 50,000 reads per second without any problem on commodity hardware. So the takeaway is that all of these problems don't show up very easily. So at that point, instead of reading through the process, which was a bottleneck, that's what we wanted to avoid, you read directly to the table. So the weight of the operation, the computation, is not in the server anymore. Before, we just said, hey, server, read the data, give it back. So that computation happened there. Now, because we read straight from the table, we, as a caller, have that problem in terms of executing that code. So there's back pressure coming back up. So our process is not affected anymore by the reads. So we completely remove the bottleneck because at that point, we, as a process that reads, we can be the slow part, but at least that process is not affected by that. So we get a good result, like concurrent writes and reads. That's a major win. We're trading strict consistency for eventual consistency, because if you have more than one process that reads and another process that concurrently, and because now we run on multi-core hardware, it's not just concurrently anymore, it's actually parallelized at the hardware level. You write in what is supposed to be the same bucket, then if you queue a few writes and read in the meantime, you may read data that is slightly stale. Now, it shouldn't be a problem because we're still talking about a cache store, but under certain circumstances, it could become something you need to take care of. And like if you're caching money, information, or things like that, then maybe you want to be sure that it's not just eventually consistent, but strictly consistent. But in most cases, this is not a problem. We still have the same problem that we had before, though. We didn't solve that at all. If this server crashes, the data is gone. The reason is that even if we create a table and that table holds the data, the process which created the table is the owner of the table. And the two things are linked. If the process crashes, it takes down all associated resources, which includes our table. So if we do something wrong, we take down the entirety of the data. At this point, there are different ways you can tackle this. The simplest one is just moving the ownership to somewhere else. We just don't let that process create the table. The table was marked as public, which means that any process can read into it. So it doesn't matter who creates it, we can always use it. So we remove the problem by saying, okay, application, entire application, when you start, first thing you do is create that cache table. So the owner of that table is the app. And if the app process is the owner, the only way that table can crash is if the application crashes, which kind of means you lost your entire service. So at that point, I feel like there's a slightly bigger problem to solve than the cache table itself. So while you restore service to the entire application, then the cache table can wait. So, and it's a simple operation in the sense that we expose creating the table as an API operation that anyone can do. And when you do it, you're the owner. So the app does it. So the app is the only thing that can affect the cache data, which is pretty good. At that point, as long as your entire node doesn't go down, then you're going to be fine. So the point of this first example was to show like two ideas basically that are important. One is where does the computation happen? That's always important, and who does what, because it boils down to one process that was doing too many things sequentially. So as long as you ask yourself that question for any computation you're working on, that should be enough to make you go in the right direction and just say, okay, do I really want to have this constraint? And the second idea is that data is owned by a process. It's always like that. So the question to ask is that, would who I want to own this data? So as long as you ask those two questions, you may naturally be led into a different implementation that has completely different trade-offs compared to the one you started with, that hopefully would fit the problem that you're working on much better, or certainly the requirements. Slightly connected to this is a second example, which has to do with log running processes. Now, let me see. OK. In this case, we're going to talk about a very, very simple game process. So imagine that you're playing a multiplayer game. And it's like you, another few people, let's say another 10 people inside this game you're playing. It's a massive multiplayer game, which means that you have the session of the game you're playing inside one specific process. It's kind of a traditional, I guess, way to model the problem in Erlang and Elixir, is that each one of these games is handled by a single process. So there's a bunch of data about it that you keep in the memory of that process. So the data is self-contained, it's just there. You want to do something with that game session, that process is the entity you're talking to. No one else will be able to help you except that process. But because of that, that process may need to do some expensive operations. Like he holds some data, but you tend to minimize that amount of state as much as you can. So if sometimes you need to compute additional data, you have to go off and grab it and put it together and give it back to the public API. Now, one way to do this normally is, again, using GenServer. Your game is a GenServer. So the state of the game could be the current score in general, the players that are involved into it, plus some other data. Really, whatever it is, it doesn't really matter. But what you want to do is we want to be able to ask this game to give you back a list of player avatars, which could be like a list of URLs to display images. The trouble is, these things are stored somewhere else. Now, for people who have never seen before this pattern, GenServer is pretty much boilerplate and callbacks. So when I want to ask the player avatars to a process ID, to a game, I use GenServer to call that operation, an operation with that name, on the process, and then I define a callback for it. And the reason is that the public API and the callback implementation could potentially sit in two different places in the code. We just see them in a single file. And also, the def player avatars part, that's run on the caller. The handle call is run in the server process. So we have effectively, this is synchronous computation. So I ask you to give me something, so I'm just going to sit and wait until you do that. But whenever the server process is doing something, it can only do one thing at a time. So anything else will sit there and waiting. So as we have a slow fetch URLs operation there, so we just say, OK, for each player, go and grab me these URLs from someone else. If that operation is slow, any other thing in this game will have to wait, including much more critical operations, like someone, I don't know, rolling a dice or someone doing something much more important. So if we just implement it this way, which is extremely idiomatic, but not particularly performant, you're going to potentially come across a few problems. So it works. It's not that it doesn't. It works. But if you fetch, you block the entire game. If you fail fetching, because you're just breaking at that point, the entire game process crashes. So for an operation that should be a straightforward, read some data and give me a bit more data, you are putting a time bomb there because you're interacting with an external service, so it's just a matter of when and not of if. It will crash at one point. So what you don't want to do, you don't want to lose the game session because that could affect at least a few people. So there are ways to get around it. There's a function in GenServer called reply. So you can explicitly, instead of using the return value of the handle call function as a return value to pass to the client, you explicitly say, okay, spawn, which means do this computation in another process, like a one-off thing that you just spawned there. It will do some stuff and die. And when you're done, reply to the original client. That from variable represents myself, the caller. So what happens here is that with a minimal change, you are shifting the computation, the heavy part of the computation, into another process, which is not our server anymore. So I'm asking you to do something. The server gets my request, spawns another process that does it, and literally after it did the spawn, it can resume processing the rest of the stuff. I'm still waiting at this point. I'm still waiting for my avatars back, and I'm not going to move until you either give them back to me or I'm going to time out. But my game process is free to just like do whatever it needs to do, and then other people can play. And because I just spawned, there's a runtime guarantee that if that fetch goes badly, my game process is completely unaffected. Like that spawn keyword operation gives you the guarantee that the two things will be completely unaffected. So I get two birds with one stone. It's because the fetch is going to run concurrently, possibly in parallel, but it's not up to us to decide. The scheduler in the runtime will handle that for us. In the worst possible scenario is concurrent. When the fetch fails, my game process is completely unaffected, so it's good. I have that resilience built in. And from the point of view of the caller, nothing changed. I'm still blocking, I'm still waiting, and I'm still going to time out in the same way if you don't reply on time. Again, we are trading a bit of consistency here because let's assume that the slow fetch is incredibly slow. Other people could join the game. By the time I get my reply back with the avatars, the list of players have changed. So hopefully that's not a problem. Again, this is very much I would say a business / requirement / design decision. It's not really it's not a solvable problem in itself unless you decide which trade-off you want to make and which feature in this case is more important. The last, actually no, sorry, let me just say quickly. So the most important idea about this example was that you always want to control where failures happen. You've got a very good built-in functionality in the language to decide where crashes, where failures happen. So it's good to use it. And the other thing is operating on state through another process does not necessarily overlap with computation. So heavy computation, it can always be parallelized as long as you have a clear idea of what it needs to be done and how you can control it in case it goes badly. The most important thing is that when you do that, you don't randomly create processes that never die. In our case, that function would die at any point. So as long as you don't create zombies, which could eventually finish the memory you have in your system, you should be fine. So the third example, which I think it's a non-concurrent example, so we're going back towards a bit single-threaded, I guess, code, is about, I'm actually not sure if it's the name I should give it to them. I'm just going to call them functional chains because that's, well, because I'm standing here, so I can call them whatever I like, I guess. But let's say that you have a series of operations. Now, jokes aside, it just means you want to do one thing after the other, chaining some functions together. Actually, I think there's something that you can do in certain libraries in JavaScript, so I'll blame that if it's the incorrect word. You have, for example, some incoming data. You're digesting user input, whether it's through an HTTP API or something like that, it doesn't really matter. And you want to do things properly, so you get some data, you whitelist the pieces of the data, possibly the format, possibly the encoding, whatever you need to do. Then you validate that that request is, it would pass validation, like you got your email address, you got your password in there, and then you want to store it. So this is pretty much anything you do in any web application that has some sort of CRUD interface. That's what you do all the time. Each one of these steps may fail for different reasons, but more often than not, it's a failure that it's a semantic failure that you want to capture. You want to do something with it. If validation fails, that's not an error. That's wrong data. It just means that you're just going to tell back, hey, I understood what you asked me to do, but this is not enough. So please send another request with more information. So from the point of view of our software, it doesn't represent something that necessarily went wrong. It just means a different outcome that is not the golden path. So at the end of the day, if we do these three operations one after the other, we need to return a value. No matter where we break, no matter where the whole thing stops, we need to return a value. So in a pure pipeline, and in terms of Elixir, I don't know if there are other languages that support this notation, but there's this fancy-looking pipe operator there, like pipe and arrow, just means get what's in the previous line, pass it as a first argument in the function. So this thing, if you wrote it differently, you would write it reverse. So it would be like, it will be store, the wraps validate, the wraps whitelist, the wraps params. So it's same as Unix, you reverse that perspective, and you can imagine you start with these params, they go through the whitelist, the result of that gets passed to validate, the result of that gets passed to store. This is really nice looking. Like you see this, if you look at a lot of Elixir code bases, you see this code everywhere. The assumption that this code does is that things go right. And when they don't, you're going to get an error that is actually going to be an argument error that says, hey, I've got this thing. You're trying to call a function, but that's not the correct type for this. Like it's not a statically typed language, but that's the type of error that you would get here. And that's a problem, because if we look at the code that consumes that module, consumes that functionality, when we look at create_user.run with params, the assumption is that it can either return two things, either a tuple that says it's OK, or and the user, so a persisted user, or an error. The problem is that error can be any of the three things that could go wrong. Either it doesn't pass whitelisting, validation, or storing. But we don't know. So we cannot tell because we structure it we just structure it like this. So even if we have a good golden path, we are effectively compressing all of the errors into one. And if something goes really wrong, and anywhere along this line we get an exception, then we just have like a massive try catch close around the entire request, which is pretty much the way that any web framework does it, so that we can serve a 500 back. So it's not particularly fine-tuned. So how do we, that's the problem. So golden path is good, fails with argument errors if things don't go properly. So what do? You can try the try-rescue approach. This is a common way to do it in a lot of languages. So you just wrap the whole thing. If something goes bad, instead of letting that bubble up as an exception, you use it as a return value. So being a return value, you can say, OK, this is an error, this is how it works, this is how it looks like. I'm going to just see what kind of error it is and decide based on that. But the problem with that is that you're hiding actual errors, actual problems. If the data storage doesn't save properly because you got a network problem with the data store, that's different from failure invalidation. And why should you smash the two things together? So all failures are treated the same. So there's Elixir ships with an incredibly nice construct, which is the width macro. So the way you read this thing is you start from the right. So you say, if whitelist params return something that matches that shape, okay and whitelisted, then move to the other line to the right. So you go down to validate. And if that does something that looks like okay valid, then you go down to the block. If at any point something returns something that doesn't match with the left, so that the return value doesn't look like that, you shortcut to the else clause. So by doing that, you effectively encode in your functions the possibility that they may fail. Now, if you've done some functional programming before, there are a lot of names for these things, which I'm not going to mention. But suffice to say, you're effectively saying this return value is not just what you care about, but it's also it went well or it went wrong. So by doing that, we have declarative methods that clearly say what could go wrong, and an entire pipeline that expresses everything, what can fail, clearly expresses that. We have control over the failure cases. If things go really bad, that will be an exception that we can handle differently. Because in the end, exceptions are different from errors. The only downside is that we need to tag these return values with OK and error. So all of this to say flexible, meaning that the whole point was that you can make little trade-offs over time to increase dramatically resilience or performance, and sometimes even clarity. So check out the standard library, because there's much more than people think, especially the Erlang standard library. And choose who owns data. That's equally important. And who runs functions, because computation is always expensive, especially if it has to do with external resources, and it can fail, which is really bad. And failure semantics are different, but you have a choice over them. So thank you. If you have any questions that will surface later and not now, you can find me at this, Twitter and email addresses. And yeah, thank you to my employer for allowing me to be here to talk about this. And yeah, thank you. Yeah. I didn't realize it was 67 slides. That's
Hi. Thanks for the talk, very interesting. The cache table, you said we have multiple readers that go direct to the table, and they don't go through the envelope or the message passing. But I think you also said the process has its own address space. So I didn't understand how the readers were getting access to the addresses. Okay, so physically speaking, your process, like the GenServer process, is here. The table looks like a static construct. Like it looks like just a data set. It's not. It's actually more than one process that runs somewhere else. And then there's you, the client caller. So when you read directly from the table, you're interacting with other processes. And more processes can read at the same time, because that table is actually a pool of processes where more than one internal process will give you back the data if you are more than one client. But between the reader and the table, is there a message being passed and returned?
There is, but it's hidden from you by the API.
Okay, thanks.
Because it is, so the only way you can get data between processes is through message passing. But normally that's hidden by functional, like a functional public API.
Yeah, thanks.
No worries.
How would you compare this? Because it seemed quite similar to me to Scala and Akka. There seems to be a lot of the same constructs.
So as far as I know, I'm not a Scala or an Akka user, but that was heavily inspired by Erlang and OTP. So there's a lot of similar constructs. The only thing I can say, or like with a certain level of confidence about that, is that all of these things are built into the runtime. While running on the JVM doesn't have a lot of these things as primitives, so they are built on top. So it's just different optimizations. But I think at the end of the day, you could approach a lot of problems probably in a similar way on both platforms. Thank you.
Thank you.